Let's now take a look at heaps and priority queues. These are two terms that are often used interchangeably, and we'll see why that is, but it's important to understand the difference between what these two things are. So let's begin by looking at a priority queue. The priority queue is an abstract data type, much like stacks and queues that we've taken a look at previously. And the priority queue maintains its elements in some order, and we'll look at a couple of different versions of that. Most implementations of this specific abstract data type provide the functions that you see here. First of all, we have an ability to enqueue an item into the priority queue. We have the ability to dequeue the highest priority item from the queue. We can also take a look at what that highest priority item is without actually removing it from the queue. And we can check if the queue is empty. Usually there are other functions, for instance, to create the priority queue, to empty it out, but these are some the basic ones with functionality. Now, since this is an abstract data type, the underlying implementation is not fixed, and as such, we can implement it in a number of ways. A heap, on the other hand, is a data structure. So a binary heap is a data structure. I'll refer to it as a heap from now on. But this is a special binary tree that has the following properties. It's got two key properties. Number one, it has a structure property. The structure property says that the tree is perfectly balanced and the leaves in the last level are leftmost in the tree. We've seen this description before. This describes a complete binary tree. The other property that is possessed by the heap is the heap order property. And the heap order property says that the value of any node in the heap is greater than or it is equal to the values of its children nodes. So this in fact defines what's called a max heap. But if we were to change that greater than to a less than, it would be considered a min heap. So therefore, if we take the above properties into account, the root of a max heap contains the largest element that's in the heap. And similarly, if we're looking at min heaps, the root is the smallest element. Now let's take a look at some figures and try to determine whether these are heaps or whether they violate one structure, one property or the other. So we can see that, so we're looking at these from the perspective of a max heap, and we can see that the everything under A is in fact a max heap. So for instance, 15, number one, it is a complete binary tree, so it has the structure property. And at any point, at any node that I take a look at, the value of that node is greater than that of its children. And again, we're talking about a max heap. So 15 is greater than 6. The second heap under A, if you look at it, it is in fact a complete binary tree. And if you look at any node, that node has a value that's greater than those of its children. So 8 is greater than both 2 and 3, 7 is greater than 6, and 10 is greater than both 8 and 7. Finally, the one on the right it's a complete binary tree, and it's also in this case a full binary tree. And 21 is greater than both 10 or 12. So we have both the structure property and we have the heap order property. Now let's take a look at B. When we look at B from the perspective of a max heap, the leftmost tree is in fact not a max heap because 15 is greater than 6, but it is now sixth child. The second one also violates the heap order property with respect to 2 being less than 8 and 3. So that violates the heap order property. Finally, the last one, we have the same issue. We're violating the heap order property because 21 is greater than 12 and thus should be 12's parent. And so as shown, that particular tree, that particular heap violates the heap order property. Now, if we look at the two trees under C, neither of them are complete binary trees. And so that's all we're looking at under the structure property is it a complete binary tree? And so we see, for instance, that the 6, for everything to be aligned leftmost, would require a node here and maybe one not here. Same thing here with this particular one. We're missing a node to make this a complete binary tree. Now, heaps are usually stored as arrays. They're data structures and they're stored as arrays. And here's an example of a heap. We're going to take a look at this array called data, and the elements are shown. And we can take that array and envision it as a tree. It would be a non-heap tree in this case by taking, by basically going in a row. For instance, we take 2 and we place it here, and we take 8 and we make it 2's left child. We take 6 and we make it its right child, and so on. 1 is next, and then 10 and 15, and then the 3, and finally the 12 and the 11. And so we have taken an array and we have laid it out as a tree. We have interpreted the contents of the array as a tree, and the arrangements of the elements basically is top to bottom and left to right as shown. Now, if we define a max heap as an array called heap, then we've got a couple of different properties, different statements that we can make about this heap. So assuming that it has n items in it, and if we look at the item at location I, so heap sub I, that value has to be greater than or equal to the value at heap sub 2 times I plus 1 and heap sub 2 times I plus 2. And so recapping this, for any node at heap I, the left child of the node is at heap 2 times I plus 1. The right child is at heap 2 times I plus 2. And the parent, if there is one, the root is the only one without a parent, the parent is at heap of I minus 1, integer divide 2. Now, elements in a heap are not totally ordered. We only know that the root is the largest in this case when we talk about a max heap, and that the descendants are less than that root, but the heap may actually lack a total order. And so the relationships between the siblings of a heap are not determined. So all we know is that if we were to follow from the root to any leaf, we have, in essence, an order, but outside of that, we do not have an order. As such, this is called a partial order. Let's use this graphic to show what we mean by a partial order. So let's take a look at a path from the root all the way to a leaf node. What we're saying is that inside this path, there is an order. And the order goes from maximum to minimum in a max heap. And so 10 is greater than 7, greater than or equal to 7, and 7 is greater than or equal to 6. If we were to take a look at another one of these, we see that there is also a partial order there. 10 is greater than or equal to 8, and 8 is greater than or equal to 2. But what we're saying is that there is no relationship between the 2 and the 3, or the 2 and the 6, or the 3 and the 6. There is no relationship between the sibling nodes or other nodes that are at the same level. So let's take a look at heaps as priority queues. So as an abstract data type, we've mentioned the priority queue can be implemented in any of a number of ways. It's actually possible to do so with linked lists, but it becomes really unwieldy as we add data. And so I can show you an example. Once we look at the mechanics of heaps, you'll see why it's not a good idea to implement it as a linked list. So it turns out that heaps are ideal for implementing priority queues because heaps are perfectly balanced trees. They're efficient to search through. And again, while we don't have a total order in this case, we do have a partial order, and as such, they're efficient to search through. Now, in order to bring this abstract data type about and actually give it an implementation, we're going to need to implement a couple of functions. So NQ and DQ are the key functions in a priority queue. So to NQ a node, we will add that node at the end of the heap, i.e. as the last leaf. And if the heap order property is lost as a result of adding it there, we will restore it by moving that node toward the root. This process is known as a heap up. To DQ a node, that is to remove a node, we will be removing the root. As we mentioned, whenever we DQ from a priority queue, we're removing the highest priority item, and that item is always at the root. So we will remove the root and we will replace it with the last leaf in the tree. If doing so violates the heap order property, we can restore that by moving that node from the root toward the last leaf. It'll stop somewhere in that path. And this is known as heaping down.